Hey guys, my name is Nikhil Maheshwar. I'm going to be one of the teachers for bioengineering this semester. And so today we want to talk about biomechanics, which is one of the parts of bioengineering. And so what we wanted to start with was a scene from a popular movie, Batman Begins. And we're going to look at a part where he tries to curl up Liam Neeson, basically. And we want to look at the mechanics of that scene. So here it is. Now, if you stop right here, you might look at this scene and think that the reason Batman is able to pull him up because he has superhuman strength. Well, Batman's actually just a normal person, so we're going to look at this, understand the biomechanics on his arm, and see why this is actually not possible.
So let's take a look at Newton's second law. So this is Newton's second law written in all its glory, and as you can see, it has three parts. The first is force, which we'll define as a push or a pull. And the second is mass, which is obviously how much stuff there is in an object. And the third is acceleration, which is the rate that velocity changes in the object. And so from these three components we use to solve all of biomechanics problems. And usually for at least starting out with biomechanics, we usually set acceleration to be equal to zero, which in turn means that this entire equation is zero. So total force is equal to zero. So now that we know that total force is usually equal to zero, we have to ask, what exactly are forces? So, of course, a force is a push or a pull. So it could be you pushing on a wall or you pulling on a wall, or, of course, good old gravity. And this here is a depiction of gravity as Einstein knew it in the form of general relativity with the Earth and the Moon. But in biomechanics, we can obviously stick to a simpler formulation of gravity. So, gravity in the classical sense comes in two flavors. The first is this. This is Newton's universal law of gravitation, and it's basically what Newton used to describe the orbits of the sun and the moon and all the planets. But on Earth, we can stick to a simpler formulation this F equals mg. Force of gravity equals mass times the gravitational constant. And gravitational constant here is 9.8 meters per second squared on the Earth. So if you weighed 10 kilograms, then you would have 98 newtons of force on you. And gravity, of course, always pushes downward. That's important to remember. Another force, of course, is normal force. And normal force is basically the force of the wall pressing against you to make sure you don't sink into it, or the force of the ground to make sure that you don't sink into the ground. So here, if you push against this box with 5 newtons, then the wall also pushes against the box with 5 newtons or to keep the box in place. And that's an important force to consider in biomechanics when things aren't moving. This is a good part to talk about Newton's second law too. So if the wall is pushing on the box with 5 newtons, then the box is also pushing on the wall with 5 newtons. And again, those are forces that you may need to account for in biomechanics. Last force is of course friction, and friction, while you may not see it that often, is still important to consider. And so friction in this basic formulation is simply the normal force times a constant. This constant usually less than 1. And then you can see that friction always opposes motion and always wants to keep things still. So friction will increase to match the pushing force until it hits this limit of the constant times the normal force. And now that we talked about some forces, we also do need to consider torque, because torque is also used in biomechanics. Now, what is torque? Torque is simply a twisting motion. So it's a force that's causing a rotation. So torque is also called moment by engineers. That's just a term we like to use. So here, torque, which is this tau term, is defined as force times the distance of the lever arm times sine theta, which is the angle between the force and the lever arm. And the way I like to think of a lever arm, like you can think of it like a door almost. Like if you're opening a door, then it's obviously easier to open door if you use more force. You can also open the door easier if you put the force further away from the hinge is here. If you put the force further away from the hinge, you don't need to use as much force. And then, of course, if you use the force perpendicularly, so the angle is 90 degrees, then you also find it easier to open the door. So those are the basics of what you need to know for biomechanics. And then let's go on to see about actually solving some problems.
Now that you have learned a bit about forces, let's apply it. First, let's start drawing a free body diagram. To do a free body diagram, you first isolate the object, and then you draw the direction of all the forces acting upon this object. For example, how would you show the forces on this person doing a headstand? So first we isolate the object. Here we only have two choices, the person or the floor, and we were told to focus on the person. So let's do that. Now let's think of the forces acting on the person. So we know this person has some sort of weight coming down. So let's call that W. But we also know that they're standing upwards. So there must be some sort of opposite force that allows them to stay up. And since we know that for an object to stay in equilibrium, you need the sum of the forces needs to be 0, F and W must somehow be the same. But can we do this? Can we simplify all the force into a single point? If we do this, we really can't understand fully the relationship between the forces that are letting this person stay up in a headstand. If you've ever done a headstand, you can feel how you are much more stable when your hands are both equally balancing your weight. Hence, the sum of the forces in your hands would be what is opposite and equal to the person's weight. So instead, it will look more like this. Okay, let's do another example. How about a foot? What forces are acting on a foot? Well, again, a person has a weight that pushes it down. But do you think your weight in a foot is evenly distributed? Should I represent it like this? For those who have arched foot, the arc does not really come in contact with the ground. So there should be less forces acting on the arc compared to the toes and the heel. And then from the toes and the heel is associated with most forces since the weight comes from the leg. And the toes act more as a balancing tool to stay standing up. So it looks more like this. Where this would be the highest and it would get lower, and this wouldn't be as high as the heel and it would get lower, where the arc there is not that many forces acting on it. And now that we've drawn our weight, there will be an opposite reaction from the floor that keeps us from sinking into the ground. So it would be just opposite and equal. So this would be the work, and this would be the normal force, which is opposite and equal. All right, so now that we know how to draw a free body diagram, let's look at a force problem. So here we have a box with lots of forces applied on it. And we're trying to figure out if you need to pull or push this box at P to keep it in place or keep it in equilibrium. Okay, so let's think about it. First, let's decide a direction that we want to try. Let's say that you want to push. So it would look something like this. And then let's divide it, since we don't really know if there'll be an angle, let's divide it into x, px, and py. Okay, so in order for this to stay in equilibrium, we know that the sum of the forces must equal to 0, which means that the sum of the forces in the x direction must equal to 0, and the sum of the forces in the y direction must also equal to 0. So let's separate it. Before we separate it, there's one more thing we need to do. We need to figure out what is a positive direction and what is a negative direction. So let's set that the positive direction is to the right and up. And as long as we stay consistent, it should be okay. So let's separate it. The only x directions, the forces in the x direction, is px and f2. So that would mean px going to the right is positive, and then it'll be minus f2. And now let's do the same thing for the y direction. So we have a positive N, a negative W, a negative F1, and a negative PY. Okay, let's plug some numbers in then. So here we have 0 equals px minus 3, which means px would be equal to 3 pounds. And in the y direction, we have 7 minus 2 minus 1 minus py, which means py equals 4 pounds. Okay, so now that we have px and py, let's try to combine them to get a final force and angle. So we have px is 3 and py is 4, and we can just use Pythagorean theorem to get our final force, which is 5 pounds. And then to get our angle, we can use SOHCAHTOA. And we know that we want to use cosine because we want to find this angle. So it will be, and that would give you 36.87 degrees. So our final force would be 5 pounds at 36.87 degrees.
So let's look at this example again and consider the force diagram on the bicep. So here we have just a basic skeletal drawing of the arm, and we're going to consider some basic forces. So first, in this direction, we're going to have the force from the bicep. This is going to be directly in the bicep muscle, and we can also call this tension. And this, in most mechanics textbook, is going to be represented by the letter T. Here, we're going to have the elbow, which is going to be our point of rotation. And this is where all of our forces are going to act upon, but they're going to rotate about that. So think about like a lever or like a seesaw almost. If you sit down, you're going to rotate about a point, and this is going to be about a point of rotation. In here, we're going to have our weight. So whenever we consider weight in terms of physics problems, we actually want to think about mass. And so when we want to like take a weight, we take mass and gravity. So we're going to talk about it in terms of mg. And in our example, this is going to be the weight of Liam Neeson. So now let's look at these forces in a typical force body diagram. We're going to have our main arm, the force from the bicep, or T, our point of rotation, and the weight from Liam Neeson. So at this point, the bicep is going to act not directly at the elbow, but it's going to act around 3 centimeters from the edge, whereas the length of the arm itself is going to be 35 centimeters. So one of the things that we're going to consider whenever talking about this problem is the mass of Liam Neeson. So the mass of Liam Neeson, just by Googling it, I found to be around 87 kilograms. And then whenever we take this to weight, by multiplying by gravity, we take mg and multiply by gravity, 87 kilograms times 9.8 meters per second squared. We get that it's about 833 newtons. So now let's calculate all of our movement about the point of rotation. So first we're going to want to calculate every force that's going to make it move in this direction. So this is only going to be our tension force. And additionally, we want all of our torques, which is all the rotations, to sum up to 0, because for in this problem, we're just going to look at the point where, say, it's all standing still. And so we're going to have our tension force, and it's going to act around 3 centimeters from this point of rotation. So we're going to multiply it by 3 centimeters. And now we're going to consider all the forces that act in the opposite direction. And so now this is going to be the weight, and it's going to act around a length of 35 centimeters because that's the length of the arm. And so we want those to be equal to each other because they're going to cancel each other out. So we're going to set this to be 35 centimeters times the weight that we calculated earlier to be 833 newtons. So now we can just solve for tension, and that's going to be 35 times 833 over 3. So this tension, whenever we calculate it, is going to be almost around 10,000 newtons, which is a little bit hard to put in context. So let's look at what the most any human was ever able to bicep curl, like a single dumbbell. The most they were able to do was a dumbbell that weighed 61 kilograms. So whenever we think about the weight of this, we're going to take 61 kilograms times gravity, which is 9.8, and this is going to be around 600 newtons. If you remember, the weight of Liam Neeson was already more. And let's look at the tension force in this bicep of the most that's ever been humanly possible. So we're going to take the same formula as before, 35 over 3 by 600. And this is going to be around 6,000 newtons. So whenever Batman is trying to lift up Liam Neeson off the edge of the cliff, he's exerting around almost 4,000 newtons extra, which is not only not humanly possible, but would absolutely tear the bicep.
All right, hi guys. So I'm going to talk about 2 real-world applications of biomechanics. So a main area of biomechanics is injury recovery. So I had knee surgery and I had to get this device that would passively move my leg up and down. So as I sat there and relaxed, it would move my leg from the down position all the way up to this flex position. So biomechanics is really useful in creating models that can reflect how the human body functions, so that machines can be created to reflect these motions. So devices like these that reflect how the leg can move up and down can be created accurately. So another big area of biomechanics is sports analytics. So in sports like baseball or golf or something where swing mechanics is really important, such that it can change the way in which the ball interacts with the environment, it's very important to understand how the human body itself can move. So this is a clip of Trevor Bauer talking about baseball mechanics. He is a pitcher for the Reds.
This is the segment where we're utilizing gravity to create energy. And how do we do that? Well, when you drift a little bit in front of the rubber and then you start to drop your body down, instead of being straight up and down, you have a little bit of tilt. And so as you drop down, there gets to be more and more and more and more tilt. And so as you're creating more tilt, you go faster towards the plate. Tilt, when I talk about tilt, I'm talking about the back leg, okay? It's, if you angle it and you start to drop, there's the force vectors push you towards the plate without you having to actually push with your back leg towards the plate.
Right, so as you can see, physics and biomechanics are very important to creating pitches and creating motion. So biomechanics is very relevant to the real world.
Hey guys, so today I'm going to be talking about 2 more applications of biomechanics to the real world. So I do a lot of yoga, and the different laws of biomechanics can be applied to yoga positions. So as you can see here, this person is doing downward dog, which is a very common yoga position. In the image to the left, it focuses on the wrist joints, and the wrist joints can be compared and analyzed using mechanical laws. So as you can see, the muscles on the underside of her arm are pulling upwards while the person's hands are pushing into the ground. And these are opposing forces that allow you to balance in this position. And in the image to the right, the highlighted muscles in red are all very important to maintain this position, because if you're on just your hands and your feet, you need to have equal forces by your hands and your feet into the ground. And you also need to be pulling your body upwards just to maintain the position without falling. So these are muscles that experience strain during that exercise. And then another example revolves just doing curls with your arms, like bicep curls. So the picture of the arm here can be compared to a lever, and the elbow is compared to the fulcrum of a lever. And your bicep has to do a lot of work pulling the weight up while the weight that's in your hand is resisting going down. So different aspects of the body can be studied using biomechanics, and this is very beneficial just in optimizing the way the body functions.